Nice. I like it. A little box for your.
Yeah.
Yeah, nice. Right, shall we continue? So yesterday's class wasn't so difficult with the IV characteristics and the simple circuits. So let's continue. Capacitors now. Capacitance and capacitor. Got that? Got that? George?
Yeah.
Yeah, okay. Got that? Yeah. Okay. So, have a look at the following picture. It's a very, very simple picture. What you've got here is a cell, not a battery, a cell. And here you have two copper plates maybe, and in here is a vacuum, usually, well, not always actually. So it's actually very simple. You just have two plates. They're close together, but they're not touching. And something very interesting happens when you have this. If I run a current through this plate becomes positively charged, and this plate becomes negatively charged. So, you know this from chemistry as well. This would have a positive charge, this would have a negative charge. Okay. Now you might say, well, what's so interesting about that? Well, the interesting thing is, if I remove the cell, then for a small time, the current will continue until these charges are gone. So it's kind of like you're storing a small current to use later. You know, it like gives you captures a little charge. Now, why might this be useful? Well, one example. Well, actually, no. We'll get to that example later. So these are called capacitors. Capacitors basically hold a small charge, and the symbol is this. So do you notice how it looks? It looks like the same for the cell. And it kind of is like a cell, except you need to charge it up first. And it usually only works for a small time, you know, a few seconds. Yeah. I'll give you an example. I don't know. Do you ever turn your TV off or turn your computer off, but the light stays on for a few seconds after you turn it off? Do you know what I mean? Like if I turn this off, this will probably blink for maybe 2 or 3 seconds. Now you might say, well, how can it blink if I turn this off? That's no power. So there's a little capacitor that is still charging, that still has some charge that can keep the current going a little bit after you cut the power. I kind of want to turn it off to SC, but you get the idea anyways, okay? So what I need you to draw, most important is the symbol, because we'll use that symbol, okay? Now, I want you to draw this, but I don't need the names, okay? You don't need to know. I mean, it's nice if you want to write it. I think you might already have these words from chemistry. Like, does anybody know what the positive plate is called? I know you've confused me. Anode, isn't it? And the negative one is the cathode. Yeah. And you've done this with Lorraine?
No.
You just knew it from high school. Okay. I heard you cycled, Joe.
No.
You didn't cycle?
No.
I'm surprised if you did. Joan told me you cycled.
I just have this one.
Ah,
Yeah, to
okay.
cover my back.
Okay.
Cycle is crazy, I think.
Yeah, you're right. You're right.
You cycle?
Oh no, not today. Not today. Joan gave me a lift in her car, which is nice. I know, right? Goodness sake.
Are you sure it's gonna stop?
Yes, it's not color about here.
How much money are you willing to bet on that? Mm-hmm. 1 o'clock, I think. Alright, continue. See a couple of people drawn. Got that? Yeah. We can continue. Great.
Do we need to write some? No.
No, it's okay. Well, you got that. Yeah, good. Okay. So the formal definition. Before I actually show it, maybe someone wants to try. What would you say a capacitor is? Yeah. We might have to say small current, but you got the idea. A capacitor. Now, you don't need to write this down. The old word for it is a condenser. Don't bother writing that down. A capacitor is an electronic device that stores electric energy. I didn't even actually say small, but it's usually small. So, don't bother writing this down. A capacitor, just this part. A capacitor is an electronic device that stores electric energy. This should remind you back home in Malaysia, right? Rainy season. Yeah.
When does it stop? The season for rain.
I don't think it really stops.
This will go on until end of.
No, it'll be rainy like this. What's this, November? Maybe you might have weather like this for another couple of weeks. Then sometime in December it'll just you might get snow.
Better than rain.
Yeah. Now you see, because we're on the coast, it's not so easy to get snow on the coast. But it'll go cold. But
Colder?
yeah. Dennis has a word for this time of the year, like it's a country word for when this rain comes. Do you have Dennis? No, okay. This is like our rainy season, you know. It'll be like this in 2 or 3 weeks. Yeah. It's what happens is in the summer we use more water, you know, because it's hot. So the reservoirs get quite low. So this is the time of the year when the reservoirs fill back up, you know. So it's necessary. It's necessary. It's also good for the plants, the grass, you know, things like this. Yeah, but it's for the soil. You see, what will happen now is the soil will get really, really wet very deeply. So then when the springtime comes and there's sun, because the ground is so wet, it means the grass will grow up very, very quickly. You know, so it's why there's so much grass here. It's because it can hold a lot of the water now, and then it'll get the sun in springtime. You know. Okay. You know, the sun is here. Yeah. Right. So we need a way to measure capacitors, how much charge they can hold, and we call this capacitance. And it's the ability to store charge. You can use a capacitor to do this. Now, the unit for capacitance is the farad, and the definition for capacitance is Q over V. So in other words, the capacitance of a capacitor is how much charge it can hold divided by the voltage across the capacitor. This is a measurement for like how big the capacitor is. So the bigger the C, the more it can hold. Okay. The unit we measure this in is the farad. But if you look at this, a farad is the same as a coulomb per volt. So one farad is one is 1 coulomb of charge held per 1 volt. That is, now for the exam, really, you just need the formula and the definition of the farad for the exam.
Without the capacitance?
Well, this formula here is what you need. Well, of course, you need to know what the letters stand for. So I don't really need you to write all of this. You can just start with the C equals Q over V.
In Asia, we drive, so we don't really care about the rate.
Yeah, you can't. I mean, that's good if you have nice roads that don't get busy when everybody tries to drive.
Either way.
Yeah. It was nice this morning because it was very nice for me because I took the car to the train station, got on the train, got a cappuccino, then got on the Lewis, and then Joan said, I'll pick you up from the Lewis stop. So I got off the Lewis about 10 minutes away. She was waiting at the Lewis stop in her car, and then we drove to the school. So I barely got any wet.
I walked
From how far?
30 minutes.
30 minutes?
That's bad.
You got good and wet. Yeah. Did you bring a change of clothes? No. Well, you'll know next time. Did you have rain gear on? No. Those hoodies aren't good in the rain. They soak up the water, huh?
I know now.
You know now, yeah. Alright, do you have that? Oh, Kim, you live on campus, don't you?
Yeah.
Yeah, that's nice. Nice. This building or the next building? So you have to, this building?
No.
The other building?
Yeah.
So you have to walk outside a little bit.
Yeah.
Yeah.
It's like quite tough.
Quite tough, isn't it? Yeah. Alright. You got that, George?
Yeah.
Okay. Right. Here is an example of where, now, okay. old example, but it gives you the idea of how a capacitor could be useful. So the flash on the camera requires a lot of energy, more energy than the battery can provide. So what do? They use a capacitor. So the capacitor charges up and then releases all the energy at once. That's how the flash works, you know. Nowadays, it's not so necessary because the phones are so advanced, you know, and the batteries in your smartphone are so powerful. It doesn't need a capacitor to have a flash, you know. Like if you press a picture to flash, do you have to wait, or will it flash instantly? Instant flash? Yeah. You see, that's because the battery's so powerful. It's like a lithium battery, you know. But you know, in the past, capacitors were useful for giving you a boost. Now there is another example of where capacitors are useful. I wonder if we can think of something else that uses a capacitor. So you need to think of something that charges up for a few seconds and releases the energy suddenly. So can you think of something that charges up and then release? What can we think of? Can you think of anything?
Laser eyes?
Laser eyes?
No, man, sorry.
I'm thinking. No. No, I don't think so. Not the laser for the eyes. But you are thinking in the right area. It is like in a hospital.
X-ray.
X-ray, very good. X-ray would be one example. That's not what I was thinking of, but X-ray would be an example, because the X-ray machine, now you've got the one I was thinking of. The X-ray machine charges up and then releases the X-ray. But the one I was thinking of was this one. Yeah.
What is it called?
Yeah, what's this called? Who knows the name? 100 points if you know the name for this. Defibrillator, yeah, that's it, defibrillator. It is. Yeah. Okay, so the capacitors are useful here. So here's a small example. Now I have no idea why I made I have to change that number. I have no idea why I made the camera 380 volts. You know, because a battery's only going to be like 1 or 2 volts, but whatever. This is the voltage, this is the capacitance, and I want the charge, I want the Q. Okay, so can you use the formula to get me the Q, please? So what does Q equal? What would Q equal? Q would equal CV. So 380 times 1,500 times 10 to the minus 6 micro. 10 to the minus 6, don't forget that.
0.57.
0.57 coulombs of charge. Okie dokie? Is that okay? That's straightforward, isn't it? Continue. Right, so there's some rules when it comes to capacitors. So the first thing is, if you have two capacitors in parallel, now, who missed class yesterday? Chow and you did. So, parallel means when they're like this. Yeah, so one capacitor and another capacitor. So, parallel looks like you have one capacitor here and one capacitor here. And this is C1 and this is C2. And you combine them together to make like a new capacitor. Okay. The total is just C1 plus C2. Okay, that's okay. Now, the students who were here yesterday, you think about that, that's a little bit odd, because yesterday with the resistors, what was the formula? Yeah, it's kind of opposite, isn't it? Okay. Now remember that voltage is the same. So yesterday we learned that the voltage here and here is the same. This is just a reminder of yesterday. The charge is additive and different. So the total charge is the charge here plus the charge here. So look, this guy has charge Q1, and this one will have a charge of Q2, and this one will have a charge of Q1 plus Q2. Kind of makes sense, doesn't it? Whoops. So like, you know, if 3 electrons come out here and 3 electrons come out here, how many electrons are here? 6. So, you know, it makes sense that the charge should just add together. Okay, so I'll let you write these 3 rules down. You got those 3? Yeah. Who has gaming laptops? You have a gaming laptop, don't you? I have a question. So, is there any easy way to fix sound and video not being synchronized? You know? So when I'm playing games, like my Lego games or whatever,
You can fix it on if you have an NVIDIA chip.
I'm not sure what I have. You know what I mean? The sound does not match at all the
Yeah.
video. Like it's off by like 3 seconds.
Oh, okay.
Yeah. It's for all the games. So to me it feels like there's a common problem. You don't... Yeah. You think it might be something within the video chip I can set.
Yeah.
So what setting would that be?
I'm not sure, but I did it for something similar. For my laptop, I did something similar. You just have to change some numbers. Search stuff on YouTube. That's what I did.
Okay. Because, you know, I think like some of the games I have, you know, like Lego, they're not exactly, you know,
Yeah.
high graphics. So I didn't think there should be any problems with this. You know, it's not like, you know, the little Lego person is so much texture that it can't render properly. All right, you got those? So next one now is series. You could probably guess what's going to happen here. So what do you think the formula for capacitance will be if they're in series? No, not the same. It's going to be different. So think about the resistors. There were 2 formulas for calculating total resistance, wasn't there? It was R equals R1 plus R2, and 1 over R equals 1 over R1 plus 1 over R2. Same thing is happening here, it's just backwards. Yeah, so this one here, it will be 1 over C equals 1 over C1 plus 1 over C2. Now, that might seem very strange, you know. You say, look, I have a capacitor here, C1, I have a capacitor here, C2, and that's like one capacitor. You might think, oh, well, that's just C1 plus C2. But it's very strange. The formula for the total is 1 over C equals 1 over C1 plus 1 over C2. It's very odd, isn't it? It's very odd. It's the exact opposite of resistors. Okay, so we can write that down. You got that? Yeah? Continue? Yeah, now this one here, you know the story with the voltage. The voltage is different and it adds. So for example, if this one has voltage V1 and this one has voltage V2, then this one here would have voltage V1 plus V2. And that's a rule that we did yesterday. Okay, so that's the second one. And the third rule is that now this one to me, of all the rules, this one at first seems the strangest. Like, this seems really strange. The charge is constant. So what you're saying here is, if this has a charge of Q, then this also must have the same charge Q. Not only, even though they're two different capacitors. Not only that, but these two charges here, if you combine them to make one capacitor, what would be the charge of this one, do you think? You think it'd be 2Q, because you have Q and Q, so the total should be 2Q. Well, it's also Q. Now, I can explain why this is, but it's very strange. So, when they're in series, the charge is constant in all the capacitors, and if you think of it as one capacitor, it also has the same charge. So that's the thing that can be confusing. Now, I'll explain why in a moment if you want to write that down. Well. That is amazing, isn't it?
Next thing you know, you're in here.
Yeah. Still not one.
Yeah, once it starts again at 1.
You guys didn't get your stuff?
No.
What stuff?
How do you do this one?
They have a food
No.
fair,
Yeah. Good
so they need to cook.
You have to sort it out tonight.
Yeah.
Last minute.
Well, it's still raining.
You'll figure something out, right? Yeah.
Cook in the morning.
A little bit.
What are you going to make for us?
I was thinking of fried banana, but
Yeah.
Banana.
there's no that kind of banana.
You need a certain kind of banana.
Yeah.
Yeah. Is it called a plantain?
I don't know, it's short.
Alright, okay, yeah. So you'll make something else then? Nice.
Like
This-
dried banana?
I don't know what it's called, but it tastes so bad if you eat it raw.
We're going to just get bananas from like.
Is it like normal
Those
bananas?
fish sweets. Those Malaysian fish sweets. You know the ones I'm talking about?
Did you say
They're sweets from Malaysia that taste like fish. Do you know the ones I'm talking? Yeah.
Really?
Yeah, yes, yeah.
Why would anyone want that?
Yeah, I know, they were terrible. I tried them a while ago. Like the worst sweet I ever had.
I think there is a.
You don't know them? Okay. They said it's a Malaysian thing. It's sweets that taste like fish.
But in Aldi, I think I have found some sweets like ginger,
Oh.
chili.
Yeah? You don't like this?
Nah.
Alright, let's have a look at why this last rule is true. So, oops. I think it's okay. Okay. So this is how a capacitor works. Let's try and pinpoint exactly what's happening here. So when we say this capacitor has a charge Q, what really happens is this one has a charge. Let's say the current is going to the right here. So this one gets a charge of plus Q, and this one here gets a charge of minus Q, for example. Now, when you turn the current off, so this gets turned off, what happens? The charge that's in here, it comes out for a short time. Why does that happen? Well, this is positive and this is negative here. So if you had a positive and negative, what would they want to do? Attract or repel? Attract. So this will want to move this direction and this will want to move this direction. So you have this movement of charge. So it's almost like it sucks some of the charge along. It pulls a bit of the charge along. So if you have just to make the picture easy, let's just say these are all protons here or something like this. If the positive moves across the negative, it's like it moves these along. It encourages a small charge to flow for a small time until these two cancel. So then, once you get back to 0, 0, there's not going to be any pull anymore. So there's not going to be any movement of current along here. Okay. So why does that matter? Well, what happens when you have two capacitors together? So let's say this is Q1 minus Q1, and this is Q2 minus Q2. If Q1 and Q2, let's draw the picture here. So positive, 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 negative, 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 positive, 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 negative, 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 negative. When I turn the current off, this and this is going to have some movement, and this is going to have some movement. But when this negative moves, it'll only cancel the positive here. You know, it's like you only care about this one and this one, because everything in the middle is cancelled as it moves through the wires. You know, like if I had a circuit here, and let's say a positive and a negative here meet, that's all that's going to happen is that they cancel. What we really care about is that this one has to move all the way over here, like it moves a current through the wire. So everything in between kind of cancels. So the total is going to be this one and this one here. But these have to be the same, because if you look back at this picture, it's gone. With a capacitor, these two have to be the same. So it's like everything in the middle cancels, and you're just left with the first one and the last one, which have to be the same to make one capacitor. Now, I'm not explaining this very well, and that's because I don't like this explanation too, because it's very difficult to understand. There are some nice animations online, I'm sure, that can explain this a bit better, because you can kind of see things moving around, and it'd be easier to understand. I try not to understand it and just accept it as true, okay? And this is my advice for you. So it's just much easier for your life if you just accept that when they're in series, the charges have to be the same, and the total combined charge is the same. If you can accept that, your life will be easier, okay? Right, so let's continue now. We just have one question to do, but it's a big one, and we'll do it together. A 100 millifarad capacitor is connected to a 200 millifarad capacitor, and they're charged using a 10 volt battery, and they're connected in parallel. Okay, so let's draw it. Here we go. So there's the first one. And it's 100 milli and 200 millifarads. And you're told that the voltage is 10 volts. They were charged up to 10 volts. Okay? Question A1, draw the circuit. So that's part 1 already done. If you want, you can put in the battery, the cell, but I won't bother, it's okay. Not necessary here. What's the total capacitance? Okay, so what formula am I using here for the total? Is it? Is it really? Are you sure? C1 plus C2. So what would it be here? 300 millifarads. Okay, part 3. What is the charge on each capacitor? Okay, so we have the formula here, C equals Q over V. So that means Q1 equals C1 V1. Yeah? So C1 is 100 milli, so that's 0.1. And what's the voltage here? We learned this yesterday. 10, yeah. So that is 1 coulomb. And Q2 is C2V2, which is 0.2 times 10, so that is 2 coulombs. What is the total charge? Okay, so what's the formula for total charge here? Yeah, Q is Q1 plus Q2. So in this case that would be 3 coulombs. And finally, what is the voltage around each capacitor? Well, it should be 10, shouldn't it? Because they're in the parallel. But I just want to confirm that it is 10. I want to show you it's 10. If I use this formula, you can see that V equals Q over C. So V1 equals Q1 over C1. Q1 is 1 and C1 is 0.1. So 1 over 0.1 is 10 volts. And likewise for V2, that will be Q2 over C2. That's 2 coulombs over, what's C2? 0.2, and that's also 10. You can see my rule checks out, that in parallel they're the same voltage. So they're both 10 volts. Okay. Now before I do part B, I'll let you write this down. You have all of this, Stephen? You have the flood story in your tradition, don't you? Noah and the flood, yeah.
No.
Is it Noah something different in?
No.
Who?
Noah.
Ah.
I thought no.
That's what I said.
No, I thought you said no.
Ah!
Yeah.
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 Now, because there's an English expression reminding me of the weather this morning. When the weather is really, really bad, like this morning, you say it's biblical. Meaning, you know, it's huge scale. But I was wondering if there's anything similar in Arabic.
Yeah.
Yeah, like because in English you can change Bible into adjective. Can you do something similar in Arabic? You know, could you go to the Quran? You could say, "Oh, the weather is really Quranic." Do you know what I mean? Like, I obviously translated, but you know, the same idea.
Like metaphors from.
Yeah. That's it. Yeah. Now it's interesting. I was talking to someone last year from Sudan as well about the metaphors, because I was explaining to him the one in English that we have, the writings on the wall. Do you know this one? The writings on the wall? Yeah, it means something is inevitable. It's about to happen. And it comes from the Bible. Anyways, there's a Quran version of it. It's something like the ink has dried or something like this.
I know.
You know what?
Yeah.
There's something kind of like this.
Yeah.
Which
There's
means
ink in it. Yeah.
Yeah, which means the same thing, that something's inevitable.
You
It's
can't
about
change
to
it,
happen.
yeah.
You can't change it. Yeah. But I just thought it was interesting. Interesting. There's a lot of stuff in English metaphors comes from two things: the Bible and Shakespeare. Like that's 90% of it comes from those two things. It's quite interesting. Okay, do we have this written down? Yeah. Right. So the B part is the same, except in series. Now I think we'll do this one together. Or what I mean is, I'll ask you to do it and then I'll check the answer. So the first part is I just want you to draw it. So I just want to see you draw and make sure you've got the picture. Now all the information is the same, okay? So it's a 100, it's a 200, and it's 10 volts around both. Is it? Yeah. Yeah, 10 around both. Okay. Good. And where are you going to put your 10 volts? Yeah, right. Now you need two though, because there's two of them.
Oh, yeah.
Yeah.
That's combined.
Ah, yeah, that's the idea, but we'll do that bit by bit. Okay. Not quite see that. That 10 volt is around volt, if you want to do like one large voltmeter. Okay, that's fine. And this one? Yeah, but you need to draw two capacitors. Two.
Oh.
Yeah. Can I see yours, Kim? Good. Oh, capacitors are like this. Not circles, please. Yes, two lines like that. Yep. There you go. Okay. Right, okay, so good job. Everybody's got this done, no problem. Calculate the capacitance on each. Oh, sorry, no, apologies. Calculate the total capacitance. Total capacitance. So what formula can you use here?
1 over C.
Yeah. 1 over C equals 1 over C1 plus 1 over C2. Man, I'm hungry. I only told you this formula 1 minute ago and I forgot it already. Because right now I'm thinking about my lunch. Got the total? So let me do the total. So it'd be 1 over 100 plus 1 over 200. So that's 3 over 200. 66 millifarads, is it?
Yes.
What answer did you get? You got 66 about?
66.
Yeah.
I got 15.
15.
Same.
Ah, yeah, but don't forget that's 1 over C. So then you have to,
Oh, 1 over 15.
yeah. Did you forget to flip it at the end? Because that's 1 over C, is 15. 66 millifarads. Is that what you're getting there? Or 0.06666 millifarads.
How do we get?
It's 1 over 100 plus 1 over 200.
Yeah.
That's equal to 15?
I got 3 over 200.
Yeah, so fine. And then you have to invert that because that's for 1 over C.
Oh.
You want to see? Are we good to continue?
What's the unit?
Well, how did you write the answer? That's MF.
MF.
Yeah. Millifarads. MF. Okay. Right, how can I get part 3? What's the charge on each capacitor?
They're the same.
Yeah, they're the same. Good. And that should equal the total. Yeah? So you can say Q equals what? CV. Do you know the total C?
Yeah.
You do. Do you know the total V?
Yeah.
You do. So you just multiply those two. So you're saying Q equals CV now. You're using yeah, Q equals CV. Yeah. So you know the C here.
Mm-hmm.
Now that's milli, 10 to the minus 3. Yeah. Times V. V is 10. Yeah. Yeah. Now just remember, milli is 10 to the minus 3. So on your calculator, look, it's like this. So 0.66 volts, coulombs. Did you get that, George? The charge part 3?
150
What you got? Q equals CV.
Oh,
Right,
I continue.
you continued your mistake down. Right. Can I continue? The answer, what is the total charge? Well, it's the same as the charge on each. Fine. These are the same answers. So lastly, what is the voltage on each capacitor? Now what could you use to get that? You could say V equals Q over C. Yeah? So what's the voltage on the first one? Q1 over C1. What's Q1? What was the charge? 0.6 over 0.1. So that's 6 volts. So I automatically know what the other one is. No. 4. Because the total should be 10. It's using the voltage adds. So for the last part you get 6 volts and 4 volts. Yeah? And Matt is checking that the second one is 4 volts by using the formula, right? And is it? Yeah. Now it's good to check these things for sure. Because then in the exam you can kind of have a feeling that you've done it right. Okay, are we okay with this now? So, you know, it's not too bad. Now you might be thinking question 5 and 6 are Stephen questions. But you would be wrong, because 5 was an exam question. A very, very old exam question from 10 years ago. Number 6 is actually a recent exam question from maybe 2 years ago. What I would like you to do, you can actually skip number 5 if you like, because it came up 10 years ago, and the person who writes the exam, I don't think they would do one as bad as number 5. And I liked it, so that's why I put it in. But number 6 is the kind of question the new guy would write. So I do need to do number 6, okay? So if you could do... if you can do these, but you can delete number 5. Well, I mean, you can do number 5 after the other ones if you like, but leave it until the end. So 1, 2, 3, 4, and 6. Yeah, just give them 5 minutes, and we'll start the next lesson.